Okay, hello again. Today we're going to talk about the second part of the fundamental theorem of calculus. This is section 5.4b in our book. And this is really the part that I would say is more useful and has more of a wide range of applications. Really, the first part, we use it to prove this, but the first part is really just useful for specific problems like we saw in the first video. So I have some problems like that for you here that are just like we had in 5.4a that use the first part of the fundamental theorem of calculus. So if you want to pause the video here, do a little bit of bell work, and give these a shot, you can, and then I'll go through them with you. All right, let's take a look at these and see how you did. So the first one, pretty straightforward. We have an accumulation function, just integral from 3 to x of sine of t dt, and we want to find f prime of x. That is the derivative of the accumulation function. So we just take that x and dump it right in there. So that is sine of x. That's it. The next one, we're looking for dg dx. So g of x is the integral from e to x. Again, e is just a constant, t squared ln t dt. So we just take the x and we dump it in everywhere we see a t. That's it. X squared ln of x. That's it. Next one, this one's a little bit different. So we have the integral from x to 0. We don't like the x on the bottom for fundamental theorem of calculus because it has to be where the function ends. So what I'm going to do is I'm going to flip it around. So we have d dx negative integral 0 to x e to the t dt, which is going to be negative e to the x, because you can pull that negative out to the front of the derivative, then take the derivative, which is e to the x, and the negative applies afterwards. The next one we're going to have to use chain rule on, because we have the integral from 3 to 2x. So I'm going to take 2x, I'm going to dump it in where that t is. So I have 2x to the 3/2 power. Then we multiply by the derivative of 2x, which is 2. That's our chain rule. Remember, you only chain on the x part, never on the t part. You just dump it in for that part. So the next one, this one has x's on the bottom and the top. So a couple ways we can think about doing this. One way is to say, well, I want to really just subtract everything before the bottom value, because if you think about this function, I have no idea what this function looks like. You could probably figure it out, but let's say it looks something like this. So if this is my root x, and this is my x to the 4th, I want the area in between. So what I can do is say, okay, I'm going to take the entire area from 0 up to x to the 4th, then I'm going to subtract off the root x. Okay, so I'm going to do the derivative of the integral from 0 to x to the 4th, 1 over root 1 minus t squared dt. Then I'm going to subtract off the integral from 0 to root x. So I'm taking away the white area here of 1 over square root of 1 minus t squared dt. So we take the derivative of each part separately. So the derivative of this guy is going to be 1 over the square root of 1 minus x to the 4th squared times 4x cubed, because we have to chain on that x to the 4th. And then it'll be minus 1 over the square root of 1 minus root x squared is just x, multiplied by the derivative of the baby function here, which would be 1/2 x to the negative 1/2. So you can clean this up a little bit more. I mean, this is 1 over 2 root x, and then here x to the 4th squared, that would be x to the 8th, but I'm out of space, so I'm just going to leave it like that. And because you don't have to do algebra, that is absolutely acceptable for an answer. If it was a multiple choice, they'd probably have some choices that had some better algebra done on that one, though. Cool. Okay, so the first part of fundamental theorem of calculus gives all kinds of fun AP problems. They give you lots of graphs like this where it's easy to find areas. They might give you some semicircles, some lines, I'll make triangles, maybe some trapezoids, and then they'll define a function. And the first thing they'll ask you is usually just to find some points. So let's say that g of x is the integral from 1 to x. So we're starting at 1, and we're going to go to x of this function. So let's say this function right here is lowercase f of x. Okay? And often what they'll actually do is they'll just put f there, because then they don't have to worry about any confusion with the t's and the x's and whatnot. So let's find some values. G of 2. So g of 2, we did this kind of in the first video, integral from 1 to 2, little f of t dt. So 1 to 2, that is this area right here. Well, that area isn't too bad. It's a quarter of a circle with radius 1. So it's 1/4 pi r squared. The radius is 1. So that is pi over 4. Nifty. G prime of 2. So the whole point of fundamental theorem of calculus is that we are looking at the derivative of g. This graph right here, f, is the derivative of g. So what helps me to do this is I make what I call the tower of functions. Every time that you have a function like this that's defined in terms of an integral, I think the tower of functions is just incredibly helpful to make. So what I do is I would start at the bottom. So I say g of x itself is the integral from 1 to x, f of t dt. That was given to us. G prime of x is the graph that we're looking at. So it's f of x. And sometimes I'll put next to that, it's the graph. And then if I wanted g double prime of x would be f prime of x, because we're just adding primes at this point. So that would be the slope of the graph that I'm looking at. So let's see here. So g prime of 2. G prime of 2, if I look at my tower of functions here, g prime of 2 is going to be the graph value when x is 2. Well, when x is 2, the graph value is 0. So don't get yourself too hung up on this, because a lot of people say, oh, it's not differentiable at 2, because this function, f, is not differentiable at 2 because it's a corner. But g is just, the derivative of g is just the graph value at that point. That's all there is to it. G prime of 3, oh sorry, g prime of 2, this was not x. G prime of 3, again, let's check our tower. If we look at our tower of functions, g prime is just the graph value when x is 3. Looks like that value is -1. Again, some people say, wait, but it's not differentiable there. F is not differentiable there, but g prime is just the graph value, which is -1. It's true the second derivative would not be defined there because this graph would not have a slope, but first derivative of g, just fine, it's -1. G double prime of 4. Uh-oh. I don't know why I chose that value. Looks like 4 actually is at the end of my interval, so that wouldn't be a value. I'm wondering if I didn't make this graph just a little bit wrong. Let's see here. Yep, that was supposed to go up a little bit further. I'm sorry about that. So this was actually supposed to go all the way to 5. I apologize. So g double prime of 4 then is going to be the slope of this graph at 4. Looks like rise over run there is +1. So if I had made my graph correctly, that would have worked out just fine. So they almost always start with something like this. What is g prime of this value? What is g double prime of this value? And then we get into some more exciting stuff. So let's take a look. What is the equation for the tangent line to g at x equals 3? Here's our g of x function. It hasn't changed. It's the accumulation function from 1 to x. So we need to find the tangent line. It doesn't change. The rules don't change. We have a point and a slope. Point and a slope. So I'm going to write out my tower of functions again. Integral 1 to x, f of t dt. That's our g of x. G prime of x is equal to this graph that I'm looking at, f of x. So it's the graph itself. The accumulation function, I guess would be worth writing here, is the area. Should have put that on my last one too. So this is the area. The derivative is the graph itself. And then g double prime is going to be f prime of x, which is the slope. Okay, so the slope here actually we already found in the last one. That's going to be g prime of 3. G prime of 3 is the same as f of 3. F of 3, -1. So we've got our slope. The point, well, x is 3. To find the y value, that's going to be g of 3. G of 3 here, I'll do that up here, would be the integral from 1 to 3 f of t dt. Because that's just the g function. So we're looking for area there. We already found this area. It was pi over 4. And then this guy right here, so if we continue to integrate to the right, it looks like the area right here is half of a unit square. So this is going to be 1/2. And because it's below the graph and we're going in the positive direction, it's negative. So the point is pi over 4, area above, minus 1/2, the area below. So pi over 4 minus 1/2. That's the y coordinate. So then, put this into point slope form. y minus pi over 4 minus 1/2 equal to the slope, negative 1, times x minus 3. And that's your tangent line. And again, it's weird because we never see the graph of g. Graphing g is difficult. You'd have to think about kind of if you're accumulating positive area or negative area. It's not easy to do. But as long as you have the tools on the derivative right here to be able to find the function values and also the derivative, you're good. Now we ask where g has a maximum or a minimum. Well, a maximum is going to happen when the first derivative changes from positive to negative. So we're looking for g prime to change positive to negative. Well, g prime is f. So I'm looking at the derivative. I want to change it from positive, which would be above the graph, to negative, which is below the graph. So there's a max at x equals 2. Why? Because we change from positive to negative. Graph values here. F values, or the derivative of g, changes positive to negative there. So max at x equals 2 because g prime, which is f of x, changes positive to negative. And then again, if I had drawn my graph correctly, we would have a minimum at 4 because we changed negative to positive. So minimum at x equals 4 because g prime of x, which is f of x, changes negative to positive. That's it. We're looking at the derivative. So don't let this fact that we're doing accumulation functions get you down. The only thing you have to worry about is how does the derivative change. You can also then tell when it's increasing, decreasing, right? G is increasing whenever f is positive, so all the way up to 2. Then it's decreasing up to 4. Kind of cool. They always love to ask about inflection points. So, tower of functions again. And it seems like overkill, but you need to be able to do this. 1 to x f of t dt. G prime of x is f of x. That's the graph we're looking at. And g double prime of x would be the slope. So that's going to be important, or f prime of x. That's going to be important for this one because an inflection point happens when there's a change in g double prime of x. Well, g double prime of x is f prime of x. So I'm looking for a change in slope. So let's mark the slopes here. At this point, we have negative slope. Then we change to positive slope. Then we go back to negative. Then we have continued negative slope here, and then we change positive at the end. So it looks like we have inflection points at x equals 0, x equals 1, and x equals 3. Because those are the two spots that g double prime of x, which is f prime of x, changes sign. Cool. That's it. A lot of AP problems that look like this. Every single time there's an AP test, they have some kind of a problem like this with an accumulation function, guaranteed. So, we've been kind of throwing this word antiderivative around, and it's a valid question to say, what the heck is an antiderivative? Because we haven't really dealt with them. We've kind of said, you can use these to evaluate integrals, but we haven't shown why, and we haven't really talked about what it is. So the whole point is, if you have, let's say f of x is x squared. We did this all of chapter 3. That means f prime of x would be 2x, right? So what we just did was we took a derivative. So that is a derivative. So an antiderivative happens when you go backwards. This is an antiderivative. So at a very base level, you're just saying, this is the derivative of some function. What function is it? Well, this is the derivative of x squared. Let's try with some other stuff. If, let's say, I don't know, f of x is sine x. Then the antiderivative, so I'm saying sine x is the derivative of some function. The antiderivative would be the antiderivative of sine x. So I think something that makes the derivative of sine. Cosine gives you negative sine, so it would be negative cosine. The derivative of negative cosine, sine x. So negative cosine x is an antiderivative for sine x. So why is this important? Because let's think about what fundamental theorem of calculus showed us, the first part. They told us that if f of x is defined as the integral from a to x, f of t dt, then f prime of x, which is the derivative of integral a to x f of t dt, is equal to lowercase f of x. So let's just write these two pieces together. We showed that capital F prime of x is equal to lowercase f of x. So what that means is if f of x is the derivative of capital F, this means that capital F of x is the antiderivative. Antiderivative for lowercase f of x. Okay? So what this means is when you do the accumulation function, we know the derivative of it is the graph that you are actually integrating. That was kind of mind-blowing to begin with. But what this means is that f of x must be the antiderivative. It's like we're going backwards. So we're taking this derivative, gives us f of x, so then the antiderivative brings us back. The antiderivative brings us back from f of x to f prime of x. Now, there is not always only one antiderivative. Like, for example, let's say we're using cosine just to make things simpler. So if, let's say lowercase f of x is cosine x, and we want an antiderivative for it. Now, the simplest one would be f of x, so we'll use capital F for antiderivative. The simplest one would be sine x, right? Because the derivative of sine x is cosine x. So the antiderivative of cosine, definitely sine. Now, tell me if this would work. What if I did sine of x plus 6? Is sine of x plus 6 also an antiderivative for cosine x? I think so, because the derivative of sine of x plus 6, that plus 6 just disappears when you take the derivative, so you get cosine. So what happens here is you get a whole family of functions, right? Basically, anything that's sine x plus some constant, we'll call it c. This might be your first plus c of calculus. So capital F of x is an antiderivative, and that's why you say an antiderivative. Usually you don't use this word, the antiderivative. We use it initially because it's like, okay, we're looking for something whose derivative makes this function. But for any function, if you're looking for an antiderivative, you can add any constant you want. Sine x plus 6, or 7, or 12, or 5,682, or e, or pi. All of those are constants that when you derive will disappear. So this is kind of the way to go. When you're looking for a general antiderivative, you can add any constant you want. So how do these help me? Well, the whole idea is then that we're looking for some kind of an antiderivative. So we have this capital F of x is the integral from a to x, f of t dt. And really, what we can do here is, because f prime of x is equal to lowercase f of x, we know that capital F of x is going to be the antiderivative. So what we can do is we can get this idea of a family of functions. So this means that the integral from a to x of f of t dt is equal to the antiderivative f of x plus c. Okay? So what's happening here is this lowercase f right here. This is our function, right? The function that we're taking the integral of, so we're accumulating it. And this capital F of x is some antiderivative because of this relationship between f and f prime, right? Basically all we're doing here is we're integrating both sides of this. The integral of the derivative is the integral of f of x. Right? So we have an antiderivative here, and it could be adding any constant that you want, and that's got to be equal to the accumulation function of our function f of t dt. So we're going to use one of our integral properties here. The integral from a to a, okay, so the integral from a to a of f of t dt is going to be equal to f of x plus c, but that's actually, we're putting in a for x. So f of a plus c. And if you integrate from the same value to itself, that has got to be equal to 0. So we're going to kind of steal this part of the equation on the right here, and we're going to subtract c. Sorry, we're going to subtract f of a. So this means that c is equal to the opposite of f of a. So we basically just solved using one value that we know information about. If you integrate from a to itself, it's going to be 0. So we have that our c value has got to be negative f of a. So we'll plug that back into here. So we have integral from a to x of f of t dt is equal to f of x, and now that we have this solved for, it's minus f of a. So whatever your a value is, if you plug that into the antiderivative, that is going to be your c value, the opposite of it. So now we're going to get a formula for any integral you ever have. The integral from a to b of f of t dt is equal to, well, if x is b now, capital F of b minus capital F of a. Since that t is a dummy variable and we now have no x's left, we're going to swap it out for an x. So we have integral from a to b of f of x dx is equal to capital F of b minus capital F of a. So let's think about what we just realized. This tells us that the area from a to b of any curve you want, a to b, if this guy right here is lowercase f of x dx, to find that area, there's a relationship between f of x and its antiderivative. All you have to do is find any antiderivative, capital F, plug in the b value, plug in the a value, subtract them, and it's going to exactly give you that area. That is pretty cool. It gives us a really powerful tool to be able to find area under curves. So here is the fundamental theorem of calculus part 2 itself. So if we have f of x is a continuous function, and capital F of x is any antiderivative, and we'll talk about why it doesn't matter which one you pick, any antiderivative for lowercase f of x, then the integral from a to b of lowercase f of x dx is equal to the antiderivative evaluated at b minus the antiderivative evaluated at a, because that's what we found out that constant was. I'll make that a little clearer there. This is fundamental theorem of calculus part 2, and it is so useful because it gives us a way to evaluate any integral from a to b of a function if we can find an antiderivative, and that's it. So that's fundamental theorem of calculus part 2. Let's take a look at some examples. So we want to integrate from negative 1 to 3 of 3x squared plus 1 dx. So 3x squared plus 1 will be shifted up, and it'll be a skinny parabola, going from negative 1, let's say that's right here, to positive 3, let's say it's like right here. So we want to find this area. Now that area is not something they taught you in geometry, right? But what we just learned is if we find an antiderivative for this guy, then it's going to be able to find the area by plugging in two values. So we need an antiderivative. For 3x squared plus 1. Now this takes a little bit of practice, and we'll learn kind of some general formulas for this. But the point is, all we have to do is think, okay, what is the thing that this is the derivative of? Well, remember, the power is always decreased by 1. So this must have started as some kind of an x cubed. And hey, that actually works out really well, because the derivative of x cubed, the 3 comes to the front, and the 3 drops down to a 2. So that's it. And then the derivative of what gives me 1? Well, this is a constant, so I'm going to need a linear function, and it's just x. So this takes some practice, takes a little bit of time. But this is an antiderivative for 3x squared plus 1. It is the simplest one I can think of. We could add a constant. I'll show you that it works in a second. But all you have to do is find an antiderivative, and x cubed plus x will work. So that means all I have to do is plug in the 3. So I'm going to do f of, so let's call this capital F of x. That's our antiderivative. So f of 3 minus f of negative 1. So that's going to be 3 cubed plus 3 minus f of negative 1. Negative 1 cubed minus 1. So 3 cubed is 27 plus 3 is 30. Minus negative 1 cubed is negative 1 minus 1 more is negative 2. 30 plus 2 is 32. So that area underneath the curve between negative 1 and 3 is exactly 32. Now let me show you why it doesn't matter which antiderivative we choose. Let's say we chose x cubed plus x plus 7. Right? Because you can add any constant you want and it's still an antiderivative. Because you take the derivative of this, it's still 3x squared plus 1. Let's try plugging it in and see what happens. So f of 3 minus f of negative 1 would be 3 cubed is 27 plus 3 plus 7. Then we subtract off, negative 1 cubed is negative 1 minus 1 plus 7. Notice what happens to the 7s. You subtract it off. Every time you do f of b minus f of a, if you have a plus c here and a plus c here, no matter what constant it is, the subtraction will take it away. So the point is, you might as well just use the simplest antiderivative, because otherwise you're just adding more work for yourself when you're subtracting. Either way, you'll get 32. Just more algebra mistakes happen when you start adding weird constants. Let's try another one. Integral 0 to pi of sine x dx. So we need an anti for sine x. We talked about this before. Antiderivative for sine x is negative cosine x. So negative cosine x will work. So we're going to do f of pi minus f of 0, which is negative cosine of pi minus cosine of, plus cosine of 0, because it's negative cosine. Cosine of pi is negative 1, so we have a positive 1, plus cosine of 0, which is 1, equals 2. We've seen this a few times. 0 to pi of sine, area of 2 underneath there. Once again, the trig functions and how they relate to each other is pretty cool. I think I might have one more. So we want the total area. The reason I bolded that is because total area is always positive. Always positive. So even though we see we have some part that's above the graph here and some part that's below, what we're going to do is we're going to have to split it up, find the integral of each piece, and then add them together, because area is always positive. If they ask for an integral, that has sign, S-I-G-N. So integral has sign. It'd be area above minus area below. Area altogether, you have to figure out which parts are above, which parts are below, and then add them together. So for this guy, we're going to have to integrate from 0 to 2 of 4 minus x squared dx. And then we'll deal with the bottom part in a second. So we need an antiderivative for this. So an antiderivative for that looks like 4 would be 4x. And then minus, so the derivative that makes x squared, it's going to have to be some kind of x cubed. But when the 3 comes to the front, I need it to cancel out. So it's got to be x cubed over 3. Then the 3 will come out, cancel out, you'll have x squared, and you'll have a 4x. Could add a constant, but it makes our life harder, so we won't. So we have our antiderivative, 4x minus x cubed over 3. We'll plug in 2 and 0. So we have 4 times 2 minus 8 thirds. Minus, hey, when I plug in 0 here, 0. Beautiful. So this gives us 8 minus 8 thirds. 8 is 24 thirds minus 8 thirds, which is going to be 16 over 3. So that's the top part here, 16 thirds. Now let's figure out the bottom. So we do that by integrating from 2 to 3. 2 to 3 of 4 minus x squared dx. So we have our antiderivative, so it's going to be 4 times 3 minus, 27 thirds, which is 9. And then we subtract off, plugging in 2. Well, we already did that once, so we're going to subtract off 16 thirds. Right? When we plugged in 2 here, we got exactly 16 thirds, so we don't have to do that math again. So we have 12 minus 9 minus 16 thirds. 12 minus 9 is 3. That's 9 thirds minus 16 thirds, which is negative 7 thirds. Now, it makes sense that it's negative because it's down below, but I want area, so I'm going to do a positive 7 thirds. Add them together. 16 thirds and 7 thirds, 23 thirds is going to be our total area. Pretty neat. So, this idea that we can find the area under any curve by using a change in the antiderivative, just subtracting those two pieces, the f of b minus f of a. Very powerful. Very powerful. So this tells us that the integral, the area, actually tells us how much the antiderivative changes over an interval. I'm not sure if I have another slide on here. I do, and I want to show you one thing on here, which is good. So your homework, 5.4 and 5a, are both going to be due on Monday. I'll see you then. Also, if you want to get the green packet, it has a whole bunch of AP problems. I think there are 6 of them, and they're similar to the one I showed at the beginning of this video. So I think they're fun. Make sure you do your tower of functions. I always do tower of functions, the accumulation function, a to x, and then you have the derivative, and that's equal to the actual graph itself. And then the second derivative, which tells you about inflection points and concavity, that's actually the slope of the graph. So I want to talk about one more thing I talked about at the end, where I was talking about the change in the antiderivative. What started this whole thing, we looked at a velocity graph, and we said if it goes straight up, we can find the change in distance by looking at the area underneath. And that makes sense to me, because if we integrate v of t, it should be a change in the antiderivative. Well, the antiderivative of velocity is position. So it'd be s of b minus s of a, which gives you the change in position exactly. So it all comes together, and it's so cool how these two fundamental theorem pieces work together and how they're going to really form the rest of the year. So I hope that you've enjoyed this and learned a little bit of something. Feel free to go back and watch any piece if you missed it. And I will see you guys on Monday. I love you guys. That's why I'm here. Have a great day.